In chemistry, as in all physical sciences, it's important that we have an agreed upon and consistent set of measurement units so that we can compare directly measurements that unique individuals make in their own respective environments. So that we're not trying to compare the lengths of individual arms, say, from different individuals trying to measure lengths. In order to compensate for this need for a consistent set of units, we use the SI system of measurement. The SI system consists of 7 base units from which can be derived all sorts of unique combinations. We're going to discuss the 7 base units, and we'll focus on 5 in particular in this course. I'm going to construct a table that shows what these base units are, what they measure, and how they're abbreviated. The first base unit that we'll talk about is the meter. We should be familiar with a meter. It measures length. The symbol for meter is lowercase m. A kilogram is the SI base unit for measuring mass. The symbol for kilogram is lowercase k, lowercase g. The second measures time and is abbreviated lowercase s. Kelvin is a measure of temperature, and this is abbreviated capital K. We use a mole to quantify amount of stuff. And we're pretty creative in how we abbreviate this, just lowercase mol. These 5 base SI units, while not a comprehensive list of SI units at this point, represent the 5 that we'll most commonly encounter in this general chemistry course. There are 2 others. There's the ampere, which measures electrical current and is abbreviated amp, or capital A. And the candela, which measures luminous intensity, how bright something is, and is abbreviated CD. We will not focus on these 2 SI units of measure in this course. In future courses, we may think about the ampere to a small extent, but we'll largely ignore the candela. So, with these 7 or 5 pertinent SI units, we can define any sort of measurement that we could ever hope to make. We can combine these base units to form so-called derived units. And even though there might be things that you could imagine measuring that aren't on this list of 5 SI base units, we can mix and match these units in order to make those measurements possible. For example, volume is not on this list of 7 SI units. So where does volume come from? If we want to measure the volume of an object, how do we do so? Suppose that you were in a math class and were asked to measure the volume of a cube. What would you do? You might start by measuring the length, the width, and the height of that cube. You'd know that volume is equal to length times width times height. And what do you use to measure those lengths, widths, and heights? You probably use a ruler, and you measure lengths, widths, heights in something like centimeters. And suppose that you measure a length of 1 centimeter, a width of 1 centimeter, and a height of 1 centimeter. The volume of this cube would then be 1 centimeter times 1 centimeter times 1 centimeter. Or 1 times 1 times 1 is 1, and centimeter times centimeter times centimeter is centimeter cubed. Because what we do to numbers, we also do to units when we perform mathematical operations. This is an incredibly important concept for us to be able to continue working with units and measure this semester. We'd say that the volume of this cube with dimensions 1 by 1 by 1 centimeter is 1 centimeter cubed. This is a derived SI unit. It's an SI unit for volume, centimeters cubed. And what's more is that this is so commonly used, especially in chemistry, that we give a volume unit its own special name. We set a definition that says that 1 cubic centimeter is exactly the same thing. A triple equal sign means exactly identical to 1 milliliter, ml. And here we define the milliliter, a unit of volume that you might already be familiar with. We can perform similar combinations with all sorts of SI base units in order to derive new units like the milliliter. Another common example that we'll see from the earliest parts of class this semester is a measure of density. Density measures how much stuff is packed into a particular volume. It is defined as amount of mass per unit volume. Mathematically, density is equal to mass over volume, where in this equation, the little m in this case stands for mass, and the capital V for volume, density, capital D. Because we measure mass in kilograms or grams, and because we measure volume in cubic centimeters or milliliters most often, we'll tend to express the units for density as, more often than not, grams per centimeter cubed, or grams per milliliter, or kilograms per centimeter cubed, or kilograms per milliliter, or kilograms per liter. Typically, we don't have to use the prefix kilo because we're not often dealing with that large a quantity of density in most materials that we'll encounter. So that begs the question, where does that prefix kilo come from in the first place? The SI system is especially useful to us because it is predicated on the metric system of counting. The metric system is a base 10 measurement system, a base 10 counting system, really, that allows us to scale measured quantities by factors of tens, hundreds, thousands, and so forth. We can make very small measurements wieldy and can do the same for very large quantities that we've measured. For example, if I wanted to measure the width of a human hair, I could measure it as, say, 0.00001 meters. But that's a really small fraction of a meter. An alternative, more wieldy way for me to say that same measurement is to say 10 micrometers. And the number 10 is a much more accessible number for us. The entirety of the SI system can be approached with this metric counting mechanism, which is based on the number 10, something that we're all already used to using because our counting system is based on the number 10 as well. By the time we get to 10, when we're counting 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, we start over again. We can do the same thing using SI units of measure, except instead of starting a count over again, we just give different magnitudes of measurements different names called prefixes. So the metric system and metric counting in general uses prefixes to indicate scale. How big or large a measurement is compared to an SI unit that doesn't have any prefix in front of it. So let's explore these prefixes and what they mean in terms of indicated scale. I'm going to start out by drawing a timeline of sorts, one where right in the middle is our SI unit without any prefix. So our SI unit of measure, like meter or liter, but not kilogram or milliliter. Just our SI unit without any prefix whatsoever goes right in the center of this timeline of metric system prefixes. And what I'll do first is think about quantities that lie to the left of this SI unit. As we go to the left, we're measuring larger and larger quantities. So things are getting larger the farther along this timeline we move to the left. The first prefix that we'll discuss is the prefix kilo. And this prefix is abbreviated lowercase k. The next prefix that we'll discuss is mega, abbreviated capital M. After this, giga, abbreviated capital G. Not only do these prefixes indicate a larger quantity than our SI unit all by itself alone does, they indicate a fixed amount of larger quantity. In other words, moving from this SI unit to the prefix kilo in front of an SI unit means a factor of 1,000-fold difference. So this is 1,000 times different. Another way to say 1,000 is with scientific notation. 1 times 10 to the third power. Moving from the prefix kilo to the prefix mega, we jump by another factor of 1,000. This is another 1,000-fold difference. Or, again, 10 to the third. And, as you might guess, going from mega to giga is another factor of 1,000 difference. Another 10 to the third power jump. What this means is that, for instance, a kilogram is worth 1,000 grams. So by placing the prefix kilo in front of grams, I now indicate that I've got 1,000 worth of those units, those grams. Placing a prefix mega in front means that I have 1,000,000 or 1,000,000 of a unit. A megagram is worth 1,000 kilograms, which in turn is worth 1,000 grams. Therefore, a megagram is worth 1,000,000 grams. The prefix giga indicates 1,000,000,000-fold increase. A gigagram would be worth 1,000,000,000 grams. On the opposite side of this SI timeline, we have units that are smaller than our SI units. So moving to the right, we deal with smaller quantities of substance. We'll talk at length about small prefixes because as chemists we tend to measure small quantities. The first metric prefix that indicates something smaller than an SI unit will be centi, abbreviated lowercase c. Next, milli, abbreviated lowercase m. Next, micro. Here, we've already used capital M for mega, lowercase m for milli, so we need an alternative. And when we need alternatives, we tend to turn to the Greek alphabet. And we'll use the Greek equivalent of the lowercase letter m, which is mu, which looks like a U but with a long tail out in front. This quantity is the Greek letter mu. We can also think about the metric prefix nano, abbreviated lowercase n, and pico, abbreviated lowercase p. For these units, we're indicating a decrease or a fraction of our SI unit. The only exception to our counting by factors of 1,000 that we'll deal with on a regular basis is the prefix centi. And just like cent or per cent or penny, we can think about centi as being a factor of 100 smaller than a base unit. So this is 100 times smaller. And I'll put 100 times here because in just a few minutes we're going to think about changing the magnitudes of measured quantities. 100-fold factor is equivalent in scientific notation to 10 to the 2. The prefix milli indicates something that's 1,000 times smaller than an SI units without any prefix in front of it. Compared to centi, though, the skip from centi to milli is only a factor of 10, or 10 to the first power. So we have this weird caveat in our centi to milli prefixes that doesn't follow the same pattern on the left-hand side of this timeline. That's okay, though, because we can just bypass centi altogether and say that milli is a fraction that's 1,000 times smaller than our SI unit, or 10 to the third times. And then going the rest of the way down this timeline, a skip from milli to micro is another 1,000-fold difference, 10 to the third power, and so too is micro to nano and nano to pico. There is one more fairly common exception used in chemistry and physics that you may see show up from time to time, but one that we will typically not use in this course to a large extent. Right in here, we tend to find an angstrom used in the measurement of length. An angstrom, abbreviated like this, indicates something that is 10 to the minus 10 in scale. And this is just an aside and an FYI. So I'm just going to get rid of this for right now, and we'll continue on with all the rest of the stuff that we've got on this timeline. These prefixes tell us how much bigger or smaller a given measurement is compared to an SI unit without any prefix in front of it. We can use this timeline to help us quickly convert from a measured quantity with a prefix in front of it to another metric prefix, or to just our baseline SI unit all by itself. For example, if we thought about measuring a quantity that ended up being, say, 1 kilometer, what's the equivalent measure to that 1 kilometer in meters? So how many meters is that worth? We can use this metric prefix timeline to help us convert 1 kilometer into an equivalent measure in meters. The way that we do that is just by counting skips along this timeline. To count skips, I'm going to look at the quantity that I have measured, that is kilometer in this case, and more specifically, just think about the prefix in front of it. The prefix in front of my measured quantity is kilo, and that's right here. The thing that I would like to convert this measured quantity into is our baseline SI unit, with no prefix in front of it whatsoever. That's right here. I see that kilo is a factor of 1,000 different than that base SI unit, and it's a larger quantity. Another way to think about this is to get from kilo here to our base SI unit along this timeline, we need to go to the right a factor of 1,000. To do that, mathematically, we can move decimal points. There's an implied decimal point after the 1 in 1 kilometer. I'm going to move that to the right a factor of 1,000. 1, 2, 3 skips is a factor of 1,000, 10 to the third power. And I'm going to fill in any vacancies that have emerged with zeros. There's a decimal point now that's at the end of this line of zeros. What I've done in this case is convert this magnitude of measure into a different magnitude of measure. It's still the same number, just with a different magnitude or prefix in front of it. I have gone from kilometers to meters. Now, what I can say is that 1 kilometer is worth 1,000 meters. Suppose I wanted to do something similar, but this time I'm going to start with 1 micrometer. So I'm going to begin from this portion of our timeline, and I want to know what an equivalent measure in meters it is to 1 micrometer. In this case, to convert 1 micrometer into meters, I can count backwards from right to left along this metric prefix timeline. I see here that a skip from micro to milli is worth a factor of 1,000, and to go from milli to centi is a factor of 10, and from centi to our baseline SI unit is a factor of 100, but we circumvented that by saying that going from milli back to our baseline SI unit is another factor of 1,000. Whichever way we combine these things, so long as we're aware of this sole exception, centi being something that is not a factor of 1,000 skip, we can say that going from micro to our baseline SI unit is worth a factor of 1,000, or 1 million, or 10 to the 6th power jump. To accomplish that, we're going to do the same thing that we did before, move a decimal point. Here it's going to be a total of 6 jumps, but because this timeline is organized so that we go from micro to our baseline SI unit by moving left, we're going to move our decimal point left. A total of 6 places. 1, 2, 3, 4, 5, 6, and fill in any vacancies and gaps with zeros. The equivalent measure to 1 micrometer in meters is 0.000001. 5 zeros after the decimal point, then a 1. This process of coming up with equivalent measures using different metric prefixes is known as coming up with a metric identity. Metric identities give us exact equivalences between different prefixed measures. A metric identity says that 1 kilometer is the exact same thing as 1,000 meters, or that 1 micrometer is exactly the same thing as 1/1,000,000th of a meter. Other ways to say this through scientific notation are that 1 kilometer is worth 10 to the third meters, or 1 micrometer is worth 10 to the minus 6 meters. So long as you can recreate a metric prefix timeline that includes these prefixes, you should have all the tools necessary to be successful when we measure quantities throughout the rest of this course and the rest of the general chemistry sequence. The last thing that I will say here about our metric system is that we can use these metric identities to set up conversions from one unit or system of measure into another convention. All we need in order to perform conversions throughout this course are identities of one form or another. For the metric system, those identities are easily accessible via that metric prefix timeline that we just looked at. To perform unit conversions, we're going to follow a template that I will introduce to you here and continue to show you through the rest of this course. And so long as you can follow this template, you should have no problem figuring out conversions, no matter how complicated they become. The process of tracking the units associated with a particular measured quantity and how they transform is known as dimensional analysis. And we can convert units using dimensional analysis and this simple template. In order to use this template, we're going to start with our given starting measured value. Our starting value will always have a corresponding set of units. So throughout this course and through the rest of your chemistry education, never report a measured quantity without units. A starting value or a measured quantity must always come with units. And this is important because in dimensional analysis, what we want to do is manipulate those units. We're going to do so by setting up what's called the conversion factor. This is a fraction, a time sign and a line. This conversion factor we'll talk more about at length in future talks. A conversion factor will always transform our starting units by eliminating them completely. In this fraction, starting units will always appear in the denominator. And target units, new units that we want to convert into, will always appear in the numerator. By multiplying our starting value with its corresponding units by this conversion factor fraction, we end up with a new quantity that's got target units. New units that we desire. The art of performing these conversions will be developing this conversion factor in the first place. So in every single case where we want to convert some starting value into a new quantity with new target units, we're going to be looking for identities. In the first part of this class, the identities that we'll learn are these metric identities just discussed. For example, let's calculate the equivalent measure in meters for a distance that's measured as 45 kilometers. Using the template that I show you up above, our starting value is 45 kilometers. I'm going to write that out first, the numerical quantity and its corresponding units. I'm going to write out a conversion factor by just drawing time sign and a line, leaving a fraction available for us to fill in a few minutes. Before we fill that in, I'm going to write out the target units, the thing that I want, which is, according to this question, meters. Somehow, I've got to get rid of kilometers and convert them into meters. My starting units need to go away. Mathematically, if I do the same thing to units that I do to numbers, then placing kilometers in the denominator of this conversion factor fraction will eliminate kilometers because dividing one quantity by itself returns just 1. We get rid of it. I'm going to place this target units in the numerator of this fraction. And I'm going to come up with an identity that relates those two. According to our metric prefix timeline, the thing that we looked at just a few moments ago, we said that 1 kilometer is equivalent to 1,000 meters. We can place those numbers in this conversion factor fraction directly next to the unit that they correspond with. 1 kilometer is equivalent to 1,000 meters. This is an identity that relates these two things. Because we said earlier that 1 kilometer is the exact same thing as 1,000 or 10 to the 3 meters, then I can just convert this into a fraction by dividing both sides by 1 kilometer. And I get this conversion factor up here. That means that all I have left to do from this point onward is math. I can plug all this into my calculator if I really want to, or I could do it in my head. I'm going to first work with numbers and then work with units. When we work with numbers, we multiply 45 times 1,000, divide by 1. That gives us 45,000. When we work with units, we multiply kilometers by meters and then divide by kilometers. Dividing kilometers by itself causes them to go away. And the only thing that we're left with at the end is meters, the units that we targeted in the first place. We'd say that the equivalent measure in meters for this quantity of 45 kilometers is 45,000 meters. And that seems trivial perhaps, but if you can get into the habit of performing this type of calculation in this manner, then by the time we get to stoichiometry later in the semester, your life is going to be much simpler.